Bless you.
Anyway.
Bless you.
Okay.
Hang tight. It's just joking.
Okay, so we have this arrangement of charges. And in part A, you're supposed to figure out the electrostatic potential at the center of the square, and you guys said 0. How did you figure that out?
Well, the potentials from two positives will cancel the potentials of the two negatives.
Okay, so does the potential of one positive cancel with the potential of the other positive? Forget about the negatives.
Oh, yeah.
Does the potential of one, what?
Potential of two positives don't cancel.
Right, they don't cancel because they're not vector quantities, so they don't cancel. But those two positive potentials exactly cancel with the negative potential. And then part B, or excuse me, part 2, it says the magnitude of the electric field, and you also have 0. Can you explain how you got 0 for that?
That's where the positive is going this way, and the other positive is going this way. Those cancel. Two vectors.
Okay.
These two.
So in that case, the vectors from the positives cancel with one another, and the vectors from the negatives cancel with one another because they're in opposite directions. Okay, so you get 0. So you get 0 for two different reasons there. One's a vector and one's a scalar. Okay, then part B, now we have a different arrangement. For part I, it says, what is the potential at the center of the square? And you guys have 0, and what's the reasoning?
Because the same as up here, the two positives that are over here cancel the two negatives that are over here.
Okay, so again, the positives are canceling out the potential from the negatives. Okay, then for the second part, it says find the magnitude of the electric field at the center. So how did you go about figuring out the electric field at the center?
So that one we did 4 times the cosine 45 because they're all 45-degree angles.
And these were vectors, right? You had to worry about. And so, Jack, when they're a vector quantity, do you actually plug in the negative sign for the charge?
No.
No.
Anyway, then, well, we basically just got the charge of 1 and multiplied it times 4 because we're not talking about positive negative right now. So we did KQ over R squared times cosine 45 times 4. For R, we used S equals root 2 over 2 because each of these is S over 2 over S over 2, which means it'd be S root 2 over 2, and solved and got 4 root 2 KQ over S squared.
So if you have it in terms of epsilon naught, it would be radical 2 times Q over pi epsilon naught S squared. It's the same answer. And then the last part, it says, in which of the two arrangements would more work be required to remove the particle at the upper right corner from its present position to a distance as long way away from the arrangement? I did mine mathematically, but I went around the groups and they had a very good over here. Duncan's group had a very good explanation of a conceptual reason, and I didn't have time to talk to you guys. You said arrangement 1, which is correct. What was your reason?
Basically because 1, it's negative close to 2 positives, so they'll be feeling the greatest force pulling it back in, as opposed to 1 that's positive and negative, negative pushing away and positive pulling it close.
Yeah, and that was the same reasoning over here, and I think that's a good conceptual reason. It's a lot faster than mine, because I actually figured out the potential, and it was a lot longer. And my guess is that's probably only worth 2 points, and that's not worth my trouble. So I like the conceptual reasoning there much better. Any questions? Okay, give them a hand. Can you please try to do some of these problems at home so we can get through them a little bit quicker? No? All right.
Yeah, I got you.
So the rest of the time is yours to work. Go ahead and put away the whiteboard.
Really good.